Oh, she's still connecting. All right. Hello. Should we just get started for today? Cool. Oh, before we start the lesson proper, actually, I wanted to make sure that everybody was in the Google Classroom, but I think that Haley, you're already in it, so I think we're good.
Okay, so today we'll speak about some algebra in classes, so some algebraic operations on classes. Okay, so first we'll start up sort of a warp riddle. Okay, so the riddle says that there are three children, John, Jack, and Renee, and they are all entitled to inherit the belongings of their father. And their father left sort of his will or a note, and then he put sort of the rules on the basis on which things will be divided or on how things should be inherited. So the first thing that there are 9 cars and 6 houses. The second condition is that if a house is declared to be inherited by 2 children, none of these two get it, and the third child gets the house. So for example, if you have house A and both 2 of these children, none of them gets the house, and the third one gets the house. Okay, so there can be no overlapping houses. And the third condition, cars will be divided equally among the three. 4, there's nothing to be inherited by both John and Renee or by both Jack and Renee. Okay, so there's nothing between John and Renee or Jack and Renee. 5, if there's any set of houses that are known to be inherited by either Renee or Jack, then they must also be possibly inherited by either Renee or John. So if you go and sort of look at a group of houses and you know that these houses are either owned by Renee or Jack, then you know that they are either owned by Renee or John also. And so the question is, how does each child inherit?
So kind of like the riddle from last time, we're gonna try
So I
and
think we'll just wait for.
yeah, we're just gonna try and solve it using basic set theory concepts. And as we go, we're gonna give you guys some time, give you some time to work on it. And if you have any questions as we go, just let us know.
Okay, so I think I'll just go through the answer or the explanation. Okay, so first we'll translate this into the set theory language. Okay, so I will just let John equals A, Jack equals B, and Renee equals C. So these will be the classes that I'm be working with. Okay. So I know from rule 4 that A intersection C is the same as B intersection C, which is just phi or the empty set. So rule number 4 says that nothing is to be inherited by both Joan and Renee or by both Jack and Renee, right? So I know that the intersection of the thing that they own is just phi. Okay, so it's the empty set. There's nothing common between A and C or B and C. Okay. Rule 5 says that A union C is the same as B union C. So here, rule 5, it says if there's any set of houses that are known to be inherited by either Renee or Jack, then they must also be possibly inherited by either Renee or John. Okay, so this is just the definition of A union B or. So just a quick, like sort of shortcut. Whenever you see that we are speaking of or in sets, so when I say or, then I usually mean the union of these two. So it either belongs to this or that. Okay, so that usually translates to union. If I say and, that usually translates to intersection, like in the fourth rule here. Okay. So from rule 5, I know that A union C is the same as B union C. Okay. We also know that all elements must belong to at least one of the three classes, one of the three children. So we will not have any house that does not belong to any of these. We will not have three houses. Okay. So that's just our basic premise. And then we'll proceed with the proof. Well, first, X belongs to A or X belongs to C if and only if or implies that X belongs to B or X belongs to C. Okay. So this is just the rule 5 here, we know that, so that union, it can be translated to x belongs to A or x belongs to C, right? And I know that this is equal to B union C. So I know that when this is true, that is true. So x belongs to A or x belongs to C implies that x belongs to B or x belongs to C. And the other way around, x belongs to B or x belongs to C implies that x belongs to A or x belongs to C. Uh, Of course, as always, whenever things get like whimsical or something like that, you can just type in the chat so I can re-explain it. Okay. So I also know that x belongs to C implies that x does not belong to A and also that x does not belong to B. So I know this from the fourth rule or rule four. Okay, I know A intersection C equals the empty set. So there's nothing common between A and C. So I know that if it belongs to C, then it certainly does not belong to A. And same thing goes for B. I know that B intersection C is just an empty set. So I know that if it belongs to C, it does not belong to B. Okay, so this is also another rule that we can just translating the rule for or deriving something from it. Okay. And then proceeding further, I know that x belongs to A implies that x does not belong to C. So that's the first thing, because again, from rule 4, A intersection C is just the empty set. So if there's something in A, then it's certainly not in C. Of course, rule 4 does not tell us anything about A intersection B, so we cannot say anything about it for now. But I know if it belongs to A, it does not belong to C. And I also know that if x belongs to A, then either x belongs to A or x belongs to C. So back in, I think, the first session, we know that if you have the O statement is true if only one of these two is true. Or like if one of these is true, then the O statement is true. Okay? So here x belongs to A or x belongs to C is true as long as x belongs to A is true. Right? So I know that if x belongs to A, this implies that x belongs to A or x belongs to C. Okay? So I also know that this would imply that x belongs to B or x belongs to C. That's the fifth rule, or as we explained it here. X belongs to A or x belongs to C implies that x belongs to B or x belongs to C. Okay, so I can just translate this part into this one. X does not belong to C and, open brackets, x belongs to A or x belongs to C would imply that x does not belong to C, so just I put this down as it is, and x belongs to B or x belongs to C. And so this would, and from this statement, I know that x does not belong to C, and at the same time, x either belongs to B or belongs to C. Okay, so these two conditions would only be true if x belongs to B. Okay, so basically what we're proving here that if x belongs to A, then x belongs to B. Okay, and we can also work the other way around. So if I start, if x belongs to B, I know that it first does not belong to C because again, C and B are disjoint or there are no common elements between B and C. And I know that if x belongs to B, then x belongs to B or x belongs to C. And again, I know that x belongs to B or x belongs to C implies that x belongs to A or x belongs to C. And so I can work the same thing backwards. Okay. If I'm going too fast, you can stop me, I guess. Okay. So from these two things, I can conclude that A equals B, or that if an element belongs to A, it belongs to B, and if an element belongs to B, then it belongs to A. Okay, so what does this tell us? So going back to the conditions, we know that if a house was inherited by two children, then none of them gets it, okay, and only the third child gets the house. So now I know that every single house that A owns, B owns, and every single house that B owns, A owns, okay? So this would mean that neither A nor B can get these houses, and C will get them. Okay, so that's from rule number 2. If in the will it is written that like Joan and Jack or A and B will get the same houses, none of these gets the houses, and Renee gets it. Okay, so so I can therefore conclude that first Renee gets all the houses and 3 cars, and the other two get no houses, and each of these get 3 cars. So for the cars thing, we already know that they are to be divided equally, and there are 9 cars, so just each child will get 3. For the houses, since every single house that was written for A was written also for B, then none of them can get the houses by rule number 2. And so Renee gets all the houses. The 6 houses will be owned by Renee or will be owned by C. Okay, so does this riddle up until now make sense before we proceed further? Or if there's any problem, you can type in the chat. Okay, the third bullet point. Okay, so we'll go through it step by step again. So x belongs to A. So this means that it implies something. If this is true, then that is true. Okay. So that is what I mean by this implies that. So I'm already starting with the assumption that x belongs to A. This would imply that first x does not belong to C. So that's from just rule number 4. Okay. I know that A intersection C is the empty set. So there is no common element between A and C, right? So if something belongs to A, it does not belong to C. So x belongs to A imply that x does not belong to C. Okay, so that's the first part. This means just and also the second condition upholds. So the second condition says that x belongs to A or x belongs to C. So when we explained the mathematical logic and the formal language, we said that there's something called the or statement. So that P or Q. So P or Q is true if any of these, if P or Q is true, okay? So if P is true, this would make P or Q true also. If Q is true, then also P or Q will be true as a whole statement. So here, if X belongs to A is true, then I know that X belongs to A or X belongs to C. This whole statement will be true, okay? And I also know from the first bullet that X belongs to A or X belongs to C implies that X belongs to B or X belongs to C. Okay, so that's just from the first bullet. So I just changed that statement from X belongs to A or X belongs to C to X belongs to B or X belongs to C. Why? Because I know that if this is true, then that is true. And then I work further, so I know from that part that X does not belong to C, and at the same time, X either belongs to B or C. And this would only be true if X belongs to B. So that would translate to X belongs to B. So just basically, when I say that this implies that, I mean, assuming that this is true, this would be also true, okay? So assuming that X does belong to A, then it certainly does not belong to C, and it certainly belongs to A or C, okay? If that is true also, so I know that if that's true, then this is true, okay? So now if this condition is true, if X does not belong to C, and X belongs to A or X belongs to C, then if that is true, then I can know for sure that first X does not belong to C, so I just left this as I mentioned before, and X belongs to B or X belongs to C, so I know that this must also be true. And this would imply at last that X belongs to B. Did this make things any clearer? Or so simply just you can evaluate the truth value of each statement uh, before and after the implication simple, okay? Before and after the implication error, okay? Did things become clearer? Or okay, great. So I think we'll just proceed further away from the middle. So we'll just go right into the new concepts. So what we'll be dealing with something called Boolean algebra, okay? So Boolean algebra, when you evaluate the mathematical operations, you care at last about the truth value of the thing. It's either true or false. So unlike the ordinary arithmetic, where you get a certain value like in addition 2 plus 2 equals 4 and such things, you get a certain value, okay? Here in Boolean algebra, we're more concerned with the truth value of the thing. Something is either true or false. We are not really concerned with a numerical value. Up until this point, we're not fully concerned with it, okay? We will get involved with it, but in later classes, not now at all. But now in Boolean algebra, what we are concerned with is the truth value of the thing. So when we perform Boolean operations, the final result is that something is either true or false, okay? And Boolean algebra applies to two branches of mathematics, mathematical logic and set theory. And in this class, of course, we are more concerned with the set theory one. So we'll be dealing with algebra of classes, okay? So the key relations in the algebra of classes is the union, intersection, and the complementation. So that's sort of A dash thing. So that's the basic operators that you'll be dealing with in the algebra of classes. We will use these to establish almost all of our theorems. Okay, so these are some basic theorems. If A and B are classes, then I know first that A is a subclass of A union B, and B is a subclass of A union B. Okay. Second, A intersection B is a subclass of A, and also A intersection B is a subclass of B. I also A subclass of B would be subclass of B if and only if A union B equals B, and A intersection B would be if and only if A union B equals B. So these are just some of the basic theorems that we'll be using in proving some of the common properties like the commutative properties and such things. So I think we'll just give you some time to try and prove these theorems using the method that we used before. So up until now, does it make sense? So I think just give you some time to prove these basic theorems using like the same method.
If you guys remember last time, we started working with Venn diagrams to visualize all the problems that we're doing. So if you're having some trouble coming up with proofs for these, try just drawing out some Venn diagrams. That'll help you think about why they're true, because once you see it drawn out, it becomes pretty obvious.
Okay, so I think we'll just proceed for the proof for the first one. Okay, so so this is the statement we are trying to prove that A is a subclass of A union B and that B is a subclass of A union B also. Okay, so that should be fairly easy. So you know if X belongs to A, this would imply that X belongs to A or X belongs to B. So which is just the A union B. So which would imply that X belongs to A union B, and that's also for the same reason like we said in the riddle. If X belongs to A is true, then this whole statement of X belongs to A, X belongs to B is true. So this would imply that, and this statement is just the definition of A union B. So just to visualize it, so here we have the set A, the set B, or the class A and class B, and I think you can see like the shadings. So we have that sort of pink area is A union B, and the blue area is just A. Uh, I think that that can help you visualize the that theorem that A is just a subclass of A union B. So A is included in A union B, right? So every element that is in A is in either A or B. So I hope that this theorem makes sense. Okay, so I think can go on to try this second one. Okay, so I think I'll just proceed with the second one. So what we're trying to prove that A intersection B is a subclass of A, or that A intersection B is included in A, and just the same thing for B intersection B, the subclass of B. So X, so we'll proceed again using the same method. X belongs to A intersection B, imply that X belongs to A and that X belongs to B. So that's just the definition of A intersection B, right? The elements that are in both A and B. So if X belongs to A and X belongs to B, this means that X surely belongs to A. And so this would mean that X belongs to A intersection B implies that X belongs to A, which is just the definition of the subclass. So A intersection B is a subclass of A because for every element that is in A intersection B, it is surely in A. So that means that it's just a subclass of A. And that's, of course, the Venn diagram to visualize it. So I think you can notice that always when I'm trying to prove a relation between this part, A intersection B, for example, or just anything before the relation, and any part after the relation, I start with assuming that there's an element in, or any element, an arbitrary element in that class, or that, for example, in here, I'm trying to prove a relation between A intersection B and A. So I start with assuming that X belongs to A intersection B, and then I see how this would reach a relation with X belongs to A, okay? So I hope that this method just makes sense, because that's the method we'll be always using, even in future theorems in set theory. So we'll always keep using the same method. So just a few more minutes to think about the third and then the fourth. Okay, so we'll proceed for the proof of the third statement. So the statement that we are trying to prove is that if A is subclass of B, this is true if and only if A union B equals B. Or that if A is a subclass of B, this implies that A union B equals B, and the same backwards, of course. So the first thing that we know that A subclass B implies that if X belongs to A, then X belongs to B. Okay, so this is just the definition of A subclass B. So I can proceed and say X belongs to A union B implies that X belongs to A or that X belongs to B. So again, that's just the definition of A union B. And this would imply that X belongs to B or that X belongs to B. So from where do I know this? I know that from the first statement, okay? So I know that X belongs to A implies that X belongs to B. So I just changed that X belongs to A to X belongs to B, okay? So this would imply that X belongs to B. So if X belongs to A union B, then it belongs to B. And of course, I can again work backwards. If X belongs to B, this would mean that X belongs to B or X belongs to B, which would mean that X belongs to A or X belongs to B, etc. So I can just say that if A is a subclass of B, then A union B equals B, and if A union B equals B, then A is a subclass of B. So this is also again the Venn diagram in order to visualize it. So here you can see the two cases. The first case where A is not a subclass of B, and the second case when A is a subclass of B. And then you can look at the relation between the A union B and such things. So I hope this helps again in visualizing this theorem. And I hope that you can also understand the formal notation, because at a certain point when we'll be dealing with infinite sets and such things, it will be really hard to visualize it. So it will really help if you can fully understand the formal notation, because there will be things that you will not be able to visualize. There's just no method to do so. So, so if there is any problem, just type it in the chat. Okay, so I think can give you just 1 or 2 more minutes to think about the fourth one. Okay, so we'll proceed for the fourth one. So that's the statement that we're trying to prove, that A intersection B equals A if and only if A union B equals B. So first I'm going to assume that this is true, that A intersection B equals A. So I know that A intersection B equals A implies that if X belongs to A intersection B, then X belongs to A, and if X belongs to A, then it belongs to A intersection B. So proceeding further, I can say that X belongs to A implies that X belongs to A intersection B, which implies that X belongs to A, and X belongs to B, which implies that X belongs to B. Okay, so I think that this point is just straightforward, just putting down all that we know from like the definitions. And so I can say that A intersection B equals A implies that A is a subclass of B, right? Because that's just the definition of a subclass. I started with the assumption that X belongs to A and reached the conclusion that X must also belong to B, okay? So that's just mean that A is a subclass of B. So keep this in mind, because we'll need it in the next steps of the proof. So that third point. So now I will let A be a subclass of B, because I need to work the other way around to prove that two things are equal, okay? Or that there is a double implication. I need to prove the implication on both sides. So I know that if A is a subclass of B, this means that X belongs to A implies that X belongs to B, okay? So X belongs, so I know first that X belongs to A implies that X belongs to B, and this whole thing implies that X belongs to A and that X belongs to B. So I started with the assumption that X belongs to A, and I know that this means that it's also in B, okay? So that's just what these three parts are saying. So this would imply that x belongs to A intersection B. So this is the definition of intersection. X belongs to A and X belongs to B. So this means that X belongs to A intersection B. Okay. So so putting these 2 points together, I can say that A subclass of B implies that A intersection B equals A. Okay. So this is just because from here I can work backwards from this step. X belongs to A intersection B means that X belongs to A and that X belongs to B, which means that X belongs to A. Okay. So here I have that A intersection B equals A, and this is based on the assumption that A is a subclass of B. So I have that A is a subclass of B implies that A intersection B equals A. And before I said that A intersection B equals A implies that A is a subclass of B. So I have that one statement, each statement implies the other one. So A intersection B equals A implies A is a subclass of B, so that's from point 3. And A is a subclass of B implies that A intersection B equals A, so that's from point 6. Okay. So using these two statements together, I can say that A is a subclass of B if and only if A intersection B equals A. Okay. And from the last theorem, I know that A is a subclass of B if and only if A union B equals B. So going back to the third, I know A is a subclass of B if and only if A union B equals B. So we already proved this, okay? So now looking at statement 7, the conclusion that A intersection B equals A if and only if A union B equals B, okay? Because I know that if A intersection B equals A, then A is a subclass of B, and if A is a subclass of B, then A union B equals B. I can also again work the other way around. If A union B equals B, then A is a subclass of B. And if A is a subclass of B, then A intersection B equals A. Okay? So that's also a visualization of it. Okay? So in this case, we do not have that A is a subclass of B, but in the second case, we have that condition applied. And you can see that A intersection B is just A. Okay? So that's just what we are trying to prove. So hopefully these 4 proofs and these 4 basic theorems make sense because we'll be using them a lot. Okay. Okay. So we'll jump to a new concept, the absorption laws. Okay, so the absorption laws are just pretty straightforward. It said that A union A intersection B equals A, and that A intersection A union B equals A. Okay, so proving these will just be easy. First, I know that A intersection B is a subclass of A, right? So we already proved this. We proved that if X belongs to A intersection B, then it surely belongs to A. And I know that A union any subclass of it is just A, okay? So that's also from the other theorem that we proved. So this is just based upon the theorem that we've already proven. So A intersection B is a subclass of A, let's just call it C. And I know that A union any of its subclasses is just A, okay? And the same thing goes for the second absorption law, okay? Again, just as usual, if there's any problem, you can type in the chat. Then we have two Morgan's laws, okay? So Monte Morgans laws are saying that A intersection B all dash equals A dash union B dash, okay? And that A union B all dash equals A dash intersection B dash. So these are just the Venn diagrams representing these two laws, okay? So you have here, you can see that all the blue part is just A union B all dash, okay? So that's all just the blue area. And that's actually the same as the A dash intersection B dash. So A dash is all the things that are not in A, B dash are all the things that are not in B. So this will just give you this blue area around, okay? And the same thing goes also for the second one. So I hope that these laws again still make sense. So, okay, so we'll start explaining some laws of arithmetic. Okay. So before we proceed on, if there is any problem, type it in the chat, and because we'll be jumping into different concepts. Okay, so one of the first, so this is just like our ordinary arithmetic. A union B equals B union A, B intersection B equals B intersection A, and these like theorems or laws are just like they are easy to prove, I think, or easy to understand. So we'll not include a formal proof here, but I think it's just pretty straightforward to realize that if X belongs to A union B, then it also belongs to B union A, and vice versa. There's the associative laws. A union B union C is the same as A union B union C. Okay, so this is just the same as in our ordinary arithmetic when we said that A plus B plus C. If I take any two and add them first, it will not matter. So the output does not matter, and here it does not matter in both the union and the intersection relations. Okay, so it's just the same. Um, there's the distributive laws, and again they apply here also. So A union B intersection C is A union B intersection A union C, and A intersection B union C is just A intersection B union A intersection C. So if you notice here, we have here a certain relation between brackets and a different relation outside. So you just take so it's just like multiplication and addition. So it's just like the same in arithmetic, but this applies for both, like the union and the intersection. The distributive laws applies, and this might be a little new, but this is called the idempotent law. So this all what this is saying that A union A is equal to A, and A intersection A is just A. Okay. So I think that these are also pretty forward laws, and I think it's easy also to prove if X belongs to A or X belongs to B, belongs to A, then X surely belongs to A. And if X belongs to A and X belongs to A, then it belongs to A. So I think it's easy to just prove these two things. So one last concept that we will need in terms of these, we're just reversing the empty and the universal classes. So A union the empty class is just A, and this again comes from the fact that the empty class is a subclass of any class. Okay, so the empty class is subclass of A, and A union any of its subclasses is just A. Okay, same thing goes for the intersection. A intersection the empty set is just the empty set. A union the universal class or the class of all elements is just the universal class, and this again comes from the fact that A is a subclass of the universal class, and we know that. So if I have that U union any of its subclasses, it's just U. A intersection U is just A. So U dash is just the empty set. So everything that's not in the universal class, so there's nothing that's not in the universal class, right? So this is just saying that U dash is the empty set. And the empty set dash or phi dash is just U. Okay. A union A dash is just U. So the set of all elements in A and the set of all elements that are not in A form the universe. Because every element is either inside the set or not in the set, or it's either inside the class or not in the class. So if I take all the elements inside a class and all the elements that are not in the class, this just gives me all the elements that are possible. And A intersection A dash is just phi or the empty set, and this is also easy to understand or easy to see why it's true, because there's no element that is both in A and not in A at the same time. So this cannot happen. So I think that's it for today. So if you have any question or any suggestion, you can just type in the chat, or you can unmute yourself and say it.